Agnello Esposito, he is a senior researcher engineer at EME Research Lab at HPE. It used to be like Cray. He was, for those who remember, he was among the first one who gave us training on Shaheen in the summer 2015. So the time flies. So Agnello, he is responsible for the Center of Excellence and collaboration with KAUST, and among other activities in the field of supercomputing. And he's involved as expert in application analysis for European procurement. He's part of the algorithm track technical committee of SC conferences, and he's involved in various activities. So Agnello has studied physics at ETH Zurich and followed by a PhD on simulation on semiconductor devices and a postdoc in computational microscopy. So he joined Cray as application analyst at HLRS in Stuttgart, and he supported several Cray systems and organized various workshops in Europe and also in Saudi Arabia. So please welcome Agnello.
So hello everybody. Thank you, Bilal and Suyash for the nice presentation. So can you hear me well?
Yes, perfect.
Very good. So yeah, for today's agenda, I will keep it a bit tighter than planned. We will start with a few general considerations around performance analysis and have a big picture of possible bottlenecks that can affect your application, together with some remedies. Then we'll deep dive directly into PERFTOOLS, which is the main performance analysis tool on HPE Cray machines. We will focus on PERFTOOLS Lite, which is the entry-level tool set or API, also for time reasons today. But this presentation actually contains much more information which you can take offline afterwards and try yourself. We will shortly touch on advanced topics like hardware performance counters, but also highlight the importance of load imbalance, communication bottlenecks, and so on. After that, a quick look at compiler feedback with the Cray compiler, and also how you can nicely visualize it together with source code in Reveal, which is also able to do variable scoping for automatic OpenMP pragma generations. And last but not least, a quick look at GDB for HPC, which is essentially GDB for MPI to be used on a large-scale machine, such as Shaheen. All right. So Bilal already gave a strong motivation on how you should consider performance analysis, and I would like to tie in there. So on the right, I think most of you are familiar with the typical cycle of scientific software development. So you implement a model, or you port a model to a new architecture. If you're lucky, it compiles right away. And if some validation test case doesn't go through properly, you usually start a debugger to have a closer look at what happens. And to be very honest here, it is very tempting at this point to just skip performance analysis because of time pressure. Let's say you have a paper you want to publish, you don't have time to analyze performance, so just skip this step and go to the implementation of the next model part. But performance does really matter. Even if you experience a performance boost after having implemented a new algorithm or ported to GPUs or whatever, it can still be that your application is doing very inefficient things most of the time. So, and in the worst case, a poor performance can also affect other users. For instance, if you have poor I/O patterns with many small files on the raster file system. In general, you want to use these very expensive resources efficiently and get as many results as you can. And this imperative applies to all scenarios. If you're new to your code, if you change the code a lot with new models, and or it has been recently ported, or even if your application is running in production since a while and you have some time to do performance analysis, please do it because it's always worth it. And it makes sense for every code scenario, such as if you're essentially wrapping your application, or you're essentially wrapping third-party libraries like TensorFlow for distributed machine learning or ScalePack for density in algebra and so on, or even if you're using fully proprietary codes like WASP, sorry, or if in the most usual case, you're using your homegrown application, which is mostly user code. Okay, here's some general remarks. We just is the best metric for your application. So assume that you are using that you are doing scattered memory references in graph analytics. Flops may not be the right metric for you. So just choose a metrics and keep it throughout your performance analysis and optimization procedure. Good practice is to choose small, medium, large versions of a test case for application analysis, where, for instance, you can choose the same model and change the grid size or number of particles in a simulation and so on. I don't recommend to use fully artificial examples like micro benchmarks to get to understand performance of your code. Just try to use a meaningful representative of your target application, which has to run at large scale. So it has to be something that you are targeting in the end. In general, start with low-hanging fruits. So start with compiler flags, manual rank reordering to optimize all-node communication, optimize libraries, obviously, huge pages, play with the ratio of NPI ranks to OpenMP ranks, and so on. And then, if you really used up all these resources, consider a performance analysis tool to identify critical code regions, guided rank reordering, and so on. Of course, it is always helpful to understand the application you're profiling, but it's not necessary. You can also be a newcomer to a code and start profiling from scratch. Actually, it's a nice way to start learning about the application. Okay. So here we have a rough overview of what the bottlenecks of an application could be. So on the upper plane, you have exclusive resources such as memory or your processor, which reside on a node, and you are the exclusive owner during an allocation. On the other hand, you also have shared resources like the network or the storage. All right, and in every case where you see, if you might identify one bottleneck in one place, which is the ideal case, you have several remedies you can try, like compiler for better loop blocking if your memory bandwidth bound, huge pages, and so on. Also for the network, you can start considering rank reordering, MPI optimization using environment variables, hybridizations, and so on. So the good scenario here is that you have one bottleneck which can be easily resolved without causing another one, okay? In the bad case, you have several bottlenecks which change over time. That's a very nasty situation where you have to spend a lot of time on one bottleneck, but another one might appear. When should you stop doing performance analysis and optimizations? Usually you can build up a model, but that's out of scope of this presentation. There is plenty of presentations around, even free presentations about this. Okay, so that's the performance, so the PERFTOOLS landscape, roughly speaking. At the top of this tool suite, you have the PERFTOOLS base module, which is loaded or should be loaded by default if you look on Shaheen, for instance. And then on the left branch, you have the so-called entry level or beginner tool suite, which has a dash light in it to show that it's beginner level. You have different flavors for different experiments like sampling, tracing, loop profiling. And I will not touch GPUs or HBM at this point, but you can have a look at the relative man pages. So on the right, we will not go into this today, but you have slides covering this as well. You have the advanced interface called PERFTOOLS, where you can really deep dive into every piece of performance analysis you would like to consider further. But for every interface, so for advanced or entry level, you have also GUIs. So in general, these are all command line tools, so it's very non-intrusive, so you can use it really at scale. You can get information on the shell from remote, it's very handy. But if you want to have further informations, or you need some more insights, you can launch one of the two GUIs here, Reveal or Apprentice 2, and we will touch very shortly about Reveal, but also show Apprentice 2. Okay, so we have already seen the two fundamental ways of doing profiling. I will just very quickly re-summarize here. So you have sampling, where you just run your code, and at the same time you take samples of your performance of your program stack at the given time intervals. Then you do statistics at the end. The main advantage here, obviously, is that it is low overhead, but the disadvantage is that you only have statistical averages at the end. On the other hand, you can do event tracing, where on every entry of a traced routine, you start a stopwatch, and whenever you exit, you stop the watch again, right? As you can imagine, this is much more intrusive. It creates more overhead, also more volumes of data to be analyzed afterwards. But the advantage is that you have very accurate data about your execution, okay? Now, there are two other experiments which are not so popular, not so viewed around, which one of these is guided tracing, where you combine sampling and event tracing. So in a first round, you do a sampling of your application to get a rough view of which routines are important. And then only for these routines, you do a tracing experiment. So it's an optimization, so to say, of the tracing to reduce the overhead of tracing itself. This is called automatic performance analysis. It's not available per se in the beginner interface, but you can have a look at it also in this slide deck later on for the advanced PERFTOOLS interface. Then also interesting is so-called loop work estimates, which is essentially a tracing experiment, but it focuses on loops only. And as we will see later on, this is a very interesting starting point if you want to port to GPUs or just to OpenMP, shared memory parallelism and so on. And this is actually available in the beginner's interface. Okay, so let's have a quick look at PERFTOOLS Lite. Okay, I hope it's not too dark on your side. It's readable.
Perfect, Danilo. Thank you.
Okay, good. So then the PERFTOOLS base module should be loaded by default. If not, you have to load it. Then just do a module load PERFTOOLS Lite, and whatever happens from now on is transparent to the user. So if you're using the compiler driver wrapper CC, capital CC, and FDN, the application will be instrumented for automatically in the background. So you just have to do a make clean make, and you will get, again, the application, the executable name you saw before or you're expecting. Here we call it app.exe. And in addition, you get an application app.exe plus oric, which is not been instrumented. So you just start, you use exactly the same command as you would have started the non-instrumented binary and capture the output of standard out. Okay, what you will see at the end of the execution is that you will get the proper program output, the one expected, and then the output from PERFTOOLS. In addition, you get also a directory which can be used for further analysis. Okay, if you want to change the name of this directory, there is an environment variable shown over here, so you can always refer to the PERFTOOLS man page if you need more explanations. Okay. Here we have the output. So I chopped it a little bit. The output of the Hymeno benchmark, which is essentially a Jacobi iteration to solve a Poisson problem. And it is very handy to do some demonstrations here. So actually the program output ends here where the arrow is. So that's just information from the Hymeno benchmark. And after that, PERFTOOLS starts reporting some information. So that's a regular output. Then we have the information from PERFTOOLS about job execution. So we run this on 8 MPI ranks. 1 thread per rank, and so on, and about the hardware used underneath. Okay, then the first interesting part here is the breakdown of routine, of number of samples according to routines. So the Jacobi routine is obviously the dominant one, and so on. So then at the end, you see some additional information on what you can further do with this profile. But essentially, that's a very low overhead way to get quickly some information about your execution. And we will dive into this messages like MPI utilization and other things later on. Okay. Now, what we have seen was sampling. But if you want to have more information or more precise information, you can do event profile. Remember, that's the more overhead related one, but you get more precise results. So you just do module swap PERFTOOLS Lite to Lite events. You just need to remove the application. You don't have to rebuild everything. You just have to remove the application and relink. And then you just restart the application and capture the standard output. Okay. What you get now is again the regular output from the application. Then again, some PERFTOOLS information about execution. And now instead of samples, you get actual times for your routine. So here, for instance, Jacobi routine took 34 seconds. And these are averages over programming elements, so over MPI ranks in this sense. Okay. Then I also mentioned another kind of experiment, loop work estimates. So that's a specialty from the Cray compiler. So you need to have the programming environment Cray loaded in the background. Then you switch to the PERFTOOLS Lite loops module. And again, you don't have to do anything in the background. So the profiler driver wrappers take care of this. You just do a make clean make and execute again by capturing the standard output. So what you get now is again what we have seen before, but now instead of samples or times broken down per routine, you have information related to every loop in your code. Okay, for instance, you see here, that's the main outer loop. That's not really interesting for us. It has been touched twice. The next 3 loops here underneath are 3 nested loops where we see the inclusive time and the exclusive time. And you see the loop trips, excuse me, the loop hit and the loop trips. And from this point, you can, for instance, think about an OpenMP port or an OpenECK port, or just in general a GPU port, if you think porting this loop specifically is suitable or not. So that's a nice starting point. All right. And for every loop, you get the routine and the line where the loop has been captured. Right. Are there any questions up to now? Otherwise, I would just switch to a demo.
Well, why good, Danilo? Yes, let's go to demo.
So are there questions or?
No, we're fine. All the questions are.
Okay, good, very good. Okay, so here I'm on an internal machine, but it's very similar to Shaheen. You will get all this training material I show over here, which contains by far much more than I will show today. But you can easily try this one on Shaheen, but I think also on Nazer. And but let's have a look at the PERFTOOLS API. And excuse me.
We'll share the links and the materials later on. So stay tuned. Okay.
Yeah, I will copy everything on Shaheen, and we'll also place the presentation here.
Excellent. Thanks.
So just to be more clear, so everything is well documented with the README markdown. So you just have to load it in the markdown view, and it's linked against every other README in the subdirectories. So here for the Hymeno benchmark, you have versions in C and Fortran. So I just choose the C version, I want to keep it clean. So what we have here is the amino source code itself as Learn job, which I will not use today because of time reasons. I am in an interactive session right now on an Haswell node. The interesting thing about amino is very flexible. So you can choose the size of the application and the number of ranks using it. So I will just choose it to be the large one and on 8 ranks, so 2 in each Cartesian direction, okay? This essentially changes the param.h include file and, excuse me, yes. I can just type make in this case. And it will create the amino.exe, which is absolutely not instrumented, nothing at all. I just want to have a dry run here to show what the output is. Okay, it should run about 10 seconds. Right. So is this too small, the font, or is it okay? I guess it's okay.
You can increase it a little bit, I think like by a couple. I can see it. But
okay.
Yeah, if you can increase it twice, I think it should be fine.
Okay, or I will just finish this one and then.
Yeah, of course. Sure.
So you see some information about the problem size. These megaflops are computed internally, so that's this has nothing to do with any performance analysis tool or anything. Just for you to see that's the CPU time, and that's some internal error of the solution, just for you. Now, what I do now is module load PERFTOOLS light, make clean, make. And as you can see, we have an additional line here showing that the executable amino.exe has been instrumented for light samples. Okay. Let's run it again. You see already some information that Cray, which is another name for PERFTOOLS, has started. So Cray and PERFTOOLS can be used interchangeably. So it's it's the same. So we have out.light here on the yeah. So the output from the amino benchmark, the regular output stops here, and then starting from here you get the Cray light performance samples outputs. Here you have in the first table you have a breakdown of user functions and relative samples to the user functions. So that's of course a very small example, and you don't see much going on in MPI. But if you want to try out, use the XL, XL, or XXL use case and run it on a larger amount of ranks on Shaheen or larger amount of nodes. Okay. Now, what we have here, sorry. So it created the output file I collected, but it also created this output directory. So what I can do here, it's all in the presentation. I say pet report my report of this directory, and I get the full report instead of the minimal report printed to standard output. Okay, you get more tables in there. Quite interesting for sampling experiments, and that's only for sampling, you get a breakdown of line numbers where most of the samples have been collected. This can be very useful if, for instance, your routine is very large, could be of interest. What here is also displayed is a summary of performance hardware counters collected for the total execution. This can be useful to give an idea or to gain an idea about memory bandwidth saturation or not. Remember that the flops on Haswell, collection of flops, is not really 100% reliable. Then another interesting report I like very much is about the output. So here, of course, we've only written to standard out, but in a more intricate case, you can really have a look at how Lustre has been used by parallel I/O. You can see if your OSTs have been saturated well, or if you have to change a little bit or play a little bit around with the Lustre parameters. Also interesting, the power and energy usage, and so on. Another interesting table is the memory bandwidth by NUMA node. So if you are using a hybrid MPI OpenMP and you don't take care of first touch policies, it can be that your threads on a NUMA node are accessing memory on another NUMA node. And this would pop up here quite clearly. So that's a way to figure out if you're doing, if you're using your memory bandwidth and NUMA locality properly, and so on. Okay, so this was PERFTOOLS Lite. So let's try PERFTOOLS Lite's events. So I just have to remove the binary and just relink. That's sufficient. And let's rerun it. So that's always the same case. Now we are doing event tracing. All right. Okay. Now you see, instead of having samples, we have actual times. Okay, we have 10 seconds for the Jacobi iteration. Okay, and again, you have useful information as before, but keep in mind, if your program is calling many small routines, the overhead of tracing can be very large. Okay, then as a last experiment, again, you get the directory for further analysis. Okay, now that we change to the PERFTOOLS Lite loops, we really have to do a make clean because it has to recompile every file again. Okay, let's have a look at the Lite loops. Here we go. Exactly. So we have a breakdown of every loop appearing in this jacobi.c file. And as you can see, if your trip count, for instance, is considerable, you may think about porting this loop to a GPU, for instance. If you don't see many trip counts here, it's usually not a good indication to port such a loop. So you usually want to break down warps and so on. You want to use all level of parallelism on a GPU. Okay. Now let me show you. So what we did here was just to collect information about all ranks. Right, but with the path report utility I've shown before, you can do a lot more after running the experiment. So let's go back to the slide deck. So are you seeing the slides again?
Yes. Well, back in the slide, yes.
Okay, so again, to summarize, we didn't change anything in the make file. What we didn't see with this very small example is that PERFTOOLS can generate for you rank reordering files to optimize all nodes. on-node communication. This will be, how should I say, in the report you will see, you will get not only the raw data, the information about what happened, but also suggestions with concrete steps how to use this suggestion. So for instance, it proposes you a rank reordering file and how to use this rank reordering file in the next execution. So what we cannot do here is to look or focus on a specific trace group like NetCDF or BLAS LAPACK. For this, you have to use the PAT report, excuse me, the PERFTOOLS utility, the advanced one. You can limit yourself, you can limit the number of ranks which are being traced by this environment variable. If you're using a very large build system, let's say with CMake that you produce many binaries, and you only want to instrument a single binary, you can use this environment variable over here, whitelist, to specify only the variables you want in a comma separated fashion. Okay, I will just go very quickly through this one. So after you have run your experiment with the directory I've shown you, you can use the PAT report utility to get a whole lot of information about the execution without rerunning anything. So here on the right, you can see, for instance, a call tree with source code line numbers and where the sources are located. Okay. Again, real quick, if you don't see an expected function in the report, there are some tricks to use here. The most successful one is the -T, which removes a threshold for routines to be shown in the report. And then what you can do as well, if you want to investigate a load imbalance, is you can start the Apprentice 2 visual or graphical user interface to check out how your ranks are distributed, but it can do a lot more. So let's quickly look at how this can be. So you have this should be this one. So
little bit big, but it's normal. Okay.
Excuse me.
Go ahead, and it's a little bit big, but continue, because like here we see that it's quite big. Okay. But go ahead.
No, it's probably because I'm just focusing on the open window and not the big one. So, but anyway, so here what I have is a client running on my Mac, and the experiment is somewhere in the US. So I'm not running any X11 forwarding or whatsoever. So here I just can access the PERFTOOLS Lite directory. Now let me start over again. Right, here we are in the test directory. I can choose any of these output directories that have been created. Let's take the tracing one. So I hope you can see it well now. From here, you can have a quick look at, for instance, the call tree. Here it's very simple, main to Jacobi or init and t. You can produce, again, the same report as shown before with other options. So it's quite a handy GUI, and it can be downloaded from Shaheen directly. The link is in the presentation itself. Okay. Yeah, let's ignore that. Okay, let's go back to the presentation. Yeah, what we haven't seen in the presentations are some advanced analysis. Which is only done if Cray or if PERFTOOLS recognizes some obvious problem, like for instance, a routine didn't use the memory bandwidth properly. And it does this by collecting memory stalls with hardware counters. And if it stalls too much, like here in the case 93%, it reports a routine to be considered further. So we haven't seen this here because it's a very small example, but you would get this one if you do pet report on the full report afterwards. We have seen this one where you improperly use OpenMP on different NUMA domains. Here you can see you have a considerable remote memory traffic between NUMA domains, which means something is going wrong with the first touch policy of your OpenMP rank. So it's a place to look at. Again, you get also hints about low vectorization of a certain routine, again, over stalls. Also about memory latency issues. So if PERFTOOLS thinks something is going wrong and it's larger than a threshold, something is not behaving properly, it will tell you. Otherwise, it will not tell you. That's to keep everything clean, so to say. The report clean. Okay. So here, just real quick, let's have a look at one of the most important things that appear when you run at scale, namely load imbalance. So again, PERFTOOLS is supposed to be very low overhead, and it's supposed to work also at a very large scale. So you can have the best hardware you can buy, but if your load balancing is not good, it will never scale out. No chance. Okay. So in the tables we have seen before, you have the time every routine spends. Here we have the user group, MPI sync and MPI, time percentage, which is obvious, but then you have the so-called imbalance time. Okay. You see it here on the third column. So imbalance time means for computational routines or IO routines, it means it's the difference between the maximum time and the average. For communication routines, it's the difference between the average and the minimum time. So if this time is large, something is going wrong in your code, and that's the first thing you should look at before even touching compilers, even touching kernels to make them faster, and so on. Another interesting point here is the MPI sync time, which in general collects the amount of time spent in waiting in collectors. So if this time is very large, again, something is imbalanced. It doesn't necessarily have to be MPI, but usually this MPI sync time pops up when some computational IO is not balanced, not well balanced. Okay.
And we have a question.
Yeah.
So what is the stall percent?
Okay, let's go back. So as you've seen before, even with the very simple analysis, we have that PERFTOOLS collects performance counters. Some of these performance counters are stalls, which is a hardware event, which means essentially the core is cycling, waiting for memory. And this is a sign, if you have many of these stalls, this is a sign that memory is not being consumed, or memory bandwidth is not being consumed properly. And for this routine, the memory stalls make 93% of the entire execution time. Okay, so it's a very bad sign.
Thanks.
Don't mix up this because it's level 1 or level 2 BLAS. It must be optimized by all means. So in this case, for instance, you can loop through something with a bad stride and use DEXP or DGMV in an improper way. Okay, that's not DEXP or DGMV used in cache or something like this. It would look differently.
Thanks.
Okay. So yes, sync time. Yes, so that's the first thing you may have to look for load imbalance. Then if you want to deep dive into communication bottlenecks, if you see that the MPI itself is imbalanced, you might want to look at a table which summarizes which function sends how many bytes in total in an aggregated fashion. You can see if you're sending many small messages, you may want to aggregate this send to change it, or even in the environment variables, you can do a man MPI, so the MPI man page, and you can change the threshold for eager versus rendezvous protocols to improve the picture. Usually, if MPI is doing very badly, PERFTOOLS will recommend you to change something with the rank reordering. So you will see an MPI observation table with instructions how to change your rank reordering. Okay, always useful is the imbalance view with the apprentice tool I've shown before. And if you really want to have a look at all the, if you want to really have a look at all the ranks separately, you can use this function, apply to the resulting output directory, and then you will get information for every single rank separately. I don't recommend this if your application is very large. Okay, so now hardware performance counters is a rather advanced topic. I just want to touch very briefly on this. So I think Kadir asked how you can see if you're using AVX2 or AVX 512 or whatever. If you know the name of the performance counter, you can export an environment variable, let's say PATRT perf counter, to this environment variable. And if your hardware supports it, it will be counted. And if you're doing an event tracing experiment, you will get the usage of this performance counter broken down by function. Okay. The same you can do with power management counters or memory stalls, whatever. You have really a huge choice of performance counters. You can have a look at this using the pot help counters, for instance, for Haswell, and look at some derived metrics or groups or whatever. Now, I have to admit, a linear map does a much better job in visualizing the temporal data of a performance counter, but you can do the same if you want with Apprentice 2. You have to set some environment variables like PATRT summary equals to 0, and then choose to collect either memory or one of the performance counters or energy usage, and then you can print it for every single rank or every single thread. You can print the function, so the number of these counters being collected over time, which can be quite handy, but in my opinion, it's quite an advanced feature, so you better spend your time in spotting problems with load imbalance. It's much more useful. Okay, let's go very quick over reveal. I don't want to use up the entire time slot. So reveal is essentially a visualization tool, but what it can do, it can also provide or produce OpenMP pragmas if you compile your code properly. So, but before we look at OpenMP pragmas, let me very quickly have a look at compiler listings. So with the Cray compiler, with the appropriate flags, you can generate, for every source file, you can generate an according listing file where it shows you what has been vectorized exactly, what has been unrolled, and so on. And you can have a look at this in a very nice way in Reveal. Okay, for that, I will just skip this one. It's for your records. You have to compile your code with a special flag, which is shown over here. This produces a program library, which you can load into Reveal, and then you can visualize your code next to these compiler listings. But much more important, what Reveal can do, what Reveal can do is to produce OpenMP pragmas automatically. And this is something I just wanted to show you real quick in a minute before we jump to GDB for HPC. Okay, I have here compiler listings. So what you can see now is that I used a special flag I showed before for Fortran, and then I also created the program library. Now let's see if reveal shows up. Nope. Try again.
So the good why it's loading. So you are going to keep the name Cray at least.
Yeah, it's popping up everywhere still.
Okay, that's good.
Yes, it takes a while until we.
No, I said about the name Cray, like it will stay, or are you going to change the naming?
The machines will change names for sure. So it's
Oh,
yeah, I mean it's EX exascale and so on.
I see.
So it's let's see if sorry for that. Let me try again. Yes, here we go. So that's again a remote client running on my laptop. So you don't need any X11 forwarding or whatsoever. So here we have the compiler listings. So for instance, Imino, you can have a look at this at the different loops in the code. Here, for instance, if you type on a loop, let's say the outermost, which is this one, you can right-click on it and type scope loop, start scoping. What you can see here is that it produced for you a scoping of every variable in the loop, and then you can produce an OpenMP pragma, which comes for free, and you can insert it into your code. Okay, just wanted to show you that real quick. So that's for the Imino benchmark, but there are other examples in the directory. So now, very quick, let me show how GDB for HPC works. So it's in the slides. So you should see my shell again. Okay, I produced, sorry. I produced a deadlock application, which is very simple. So I'm doing a very bad MPI receive, MPI send configuration. So I just compile it without any, I mean, we don't need any anything loaded in the background regarding profiling.
That's why, like on Shaheen, we have to remove also the Darshan.
Okay, and also Xalt maybe.
Xalt, yes, also yes.
Okay. So what we have here. So just very quick. I'm sorry for running late here. You launch GDB for HPC like this. You get a prompt, and then you can easily launch the application. You can do a backtrace to see where you are. We are now at the MPI init. Let's continue. Then we are in the deadlock, probably. Let's halt the application, backtrace. Yes, so rank 1 is waiting in deadlock at line 30, and the other one is waiting at line 25, which is twice the MPI receive call, which is a bad choice to do. So I should have done first send and then receive on another rank. Okay. Just very quick, in a second, maybe you can also attach to an already running application. Sorry. For that, you need the job step number with stat, right? Excuse me. Then you can just type attach the context. And it attaches to the program and halts the program. So again, we are in the deadlock at line 25 and at line 30. Okay. So again, sorry for running late, but I just wanted to show you all these things. Please have a look at the slides. So there is also more information about pad run, for instance, which is very useful if you run an application you don't have access to. I mean, the source. So you can just launch it with pad run, and then you get information about rank placement you can change and so on. Let's say WASP or something which is proprietary 100%. Okay.
Okay. Sounds good. Thank you very much, Aniello.